All right, so my name is Fadi Abushala. I'll be talking today about the leveraging the RISC-V efficient trace standard, which I'll be referring to as eTrace. A little bit of the agenda. Why do we trace? What are some of the trace basics? I'll talk about the eTrace standard, and I'll also talk about an eTrace IP encoder developed by Siemens in a summary. All right, so as you all know, there has been and continue to be an insatiable demand for more compute, exponential increase in design complexities. We are packing more and more gates in each chip and more functionality. And sometimes you wonder, well, how do you debug the software that is rising in complexity along with the devices that are on this chip? In the old days, you'd be able to do halt, single step, run, to figure out where is the bug in your software. With so many devices running simultaneously, bugs are dependent on device-to-device interaction, and if you halt and single step, those bugs disappear. So what you end up needing is some kind of system that does real-time trace and debug while the system is running system software in order to find those bugs, in order to help you go back and figure out what happened at which point and why. For the sake of this conversation, I'm going to take this block diagram of one of our customers and discuss why do we trace. This is one of the many large, very complex designs. In this particular design, there is 16 processors with 16 co-processors over 5 clusters. So there is a total of 80 cores and 80 co-processors running simultaneously. There are crypto blocks, accelerators. There are hardware accelerators as well. And this is running at 1.2 gigahertz. It happens to have a 40-bit program counter. So they were able to count that the amount of raw trace data being collected from all these cores is equal to 480 gigabytes per second. How do you manage that level of data, and how do you debug? So that's why you need to trace. And where do you trace? I put this picture together to show that the trace encoder actually sits right there inside the chip. At Siemens, we have a RTL encoder that is instantiated part of the SoC. And the idea is to collect the trace, encode it, which is to compress it, bring it off chip in order for you to be able to decode it in software and be able to see in an IDE what is going on in your system. This helps with forensic debugging, code profiling, code coverage, Heisenberg, and bugs that occur every once in a while and that are very hard to catch. All right, so processor branch trace is one of those traces that is efficient and where only branches are reported, such as jumps, calls, returns, interrupts, exception. Sequential instructions are not reported. Therefore, the amount of data that you collect and transport off chip is reduced, is compressed. And this achieves a very high compression. So this is a little simulation of what's going on in this little piece of code. You always have to start reporting the start address. And then the next sequential instructions are not reported because they are sequential. Now there's a branch not taken, but you still reported, followed by multiple sequential instructions that are not reported. Then there's a branch taken and reported. Go back, more instructions, not reported. And then finally, the branch not taken. So it shows that in a sequence of instructions, you only report a certain number of data so that you can take this off chip and reconstruct the program flow and figure out what happened in your design. this is a picture just showing that the eTrace standard is able to compress data better than other trace protocols. And it shows here that on the average, the compression is down to 0.1 bit per instruction. This enables you to do higher compression and trace longer, trace faster, trace more, and transport the data off chip with less bandwidth. Siemens, previously the division Ultrasoc, started working on this eTrace with Seagate, and back in 2016, I believe, and they developed the eTrace spec, donated it to the RISC-V International community, and most of the features there were donated back by Siemens. In the spec itself, there are mandatory features listed here, and there are optional features listed on the right, such as implicit return mode, branch prediction mode, and jump target cache mode that are optional, but they are part of the standard. And Siemens happens to also have a cycle accurate trace that is currently not part of the standard, but it is implemented. All these features are implemented in the Siemens eTrace encoder. All right, this is a little bit about implicit return and branch prediction and jump target cache. I'll go through this. I will not go through this because there's more interesting slides coming next. So this picture here shows our engagement with Seagate, but mostly it shows that the problem that Seagate was looking for is that they had, this example shows a 50 terabyte hard disk drive running at high speed, and with the heads needing to locate data to read and to write, needing to be positioned within 2.4 nanometer accuracy. So imagine that. This is not inside of a chip. It is a physical location on the hard drive with 2.4 nanometer accuracy. That's kind of crazy. The amount of processing that happens in order to ensure this accuracy is huge. And working with Seagate, they were able to, with the real-time processing system that they have, they were able to improve the process of the design of their system under constraints such as power, space, and cost. So the overall result of improving their design was a 3x reduction in their disturbance detection filter and basically reducing the computational cycle 3 times compared to their previous design. All right, so I'm going to finish with an example of how trace can be implemented in a general SoC, in a generally complex SoC that has here a cluster of Andes RISC-V cores, DSP cores, DRAM controllers, GPU clusters, all connected via a NOC. This is just a representation of a complex chip. You could have much more devices there, but this is just for illustrative purposes. Where the trace encoder fits is shown right here, where the trace encoder is connected to the trace port of the Andes RISC-V core and is connected to the message engine infrastructure provided by Siemens. On the bottom section, all the IP modules that I showed are all provided by Siemens. On the top, it is your customer design. We also provide a run control module that enables you to run, halt, single step, etc. And we have our own messaging infrastructure that enables you to connect with the outside world via either a JTAG or USB 2 port, USB 3, or an Aurora SerDes. And not all customers need to have all 4 ports. Some customers have 1, some have 2. There's also an AXI communicator module shows on the right. And there's an SMB, which is a system memory buffer IP module that enables you to collect the trace, collect the data that's been that's been running in the chip that the IP is collecting, store it temporarily in memory before you can take it off chip later on. Now, in addition to providing trace and run control to the Andes core, you're also able to have additional visibility into the rest of the chip. Shown here is run control on the DSP, status monitor running, looking at the custom logic. The status monitor is nothing more than a logic analyzer on a chip. Bus monitors are transaction-aware monitors that look at different part of the buses, provide this data off chip. And then static instrumentation is a module that enables you to do basically code profiling. All connected via this tree structure of our messaging infrastructure. I can answer more questions on how this all works and how it's built. We have a booth right outside if you have more questions. Now, in the complex world of designs, many times there are other processors in the system. If your design happens to have non-RISC-V cores or cores that are RISC-V as well as non-RISC-V cores, we also have the ability to extend and coexist with other CPU trace modules and connect them also to our messaging infrastructure. So this is basically an entire picture showing a large complex chip with the modules that are provided by Siemens, and then in particular focus on the enhanced tracer encoder. And if you have any questions, let me know, because the next slide is a summary slide. So important here is to understand program behavior in complex systems. That's very challenging. Non-intrusive full-speed observation of program behavior is required. The efficient trace for RISC-V addresses this problem. And there are optional encoding modes that offer significant benefits. Siemens offers a complete family of embedded analytics IP modules that are compliant with this RISC-V standard, that provide visibility and control on the RISC-V cores, as well as provide visibility into the rest of the chip. What this does is that it enables you to optimize your system software. We are looking for software bugs more than hardware bugs. You're able to slash design validation cost. And one thing that is important to note here is that in addition to doing in-lab device bring-up, these IPs are RTL IP modules that are instantiated in RTL. They are synthesized that stay in the chip, take about 1% to 2% of the chip area. And they go to gates and they go to silicon so that you're able to continue to collect trace data or performance monitoring data when the devices are installed in boxes, on cards and boxes, and deployed in the field. Whether it is in 5G, in data centers, in AI, automotive, storage, you're able to continue to monitor the performance of your device in the lab as well as when it is released and deployed in the field. Any questions? Good. I only take easy questions. So, all right, thank you very much. Please meet me at the booth outside if you have more additional questions or you have a specific topic you want to discuss. Thank you.